All right, my friends, welcome back. We're going to spend the first little bit talking about cyclohexane conformations, and we'll move on to stereochemistry. Just a reminder of where we are. We have an exam planned for next week. I know that's really fast after this previous exam, but that's the problem in a spring semester. Later today, I will email all of you who have taken the exam a link to a video that will explain the right answers to all the questions. You should be able to see your responses and items missed on the Testing Center website, and then you can see sort of what you did wrong. The best thing you can do to prepare for the next exam is to find out precisely those things that you struggle with, that you're weak on, and then practice them. To that end, study guides for chapters 4 was already up, 5 and 6 and 7 and 8 are already up. There is almost zero chance we're going to get to chapters 7 and 8 by the exam. I will write the exam to test only on the things that we've covered. So we'll have to be a little bit flexible with the plan. The practice exam is also up. That practice exam covers all the way through chapters 7 and 8. You only have to do right now the parts that are relevant. So feel free to, when the time comes, report that you've completed the practice exam, even though there will be some of it that we won't do until the next section. All right, so yes?
When are you going to post the answers?
To the practice exam? Did I not do that yet?
Oh, have you?
I haven't. I posted the practice exam, but not the answer key. Yeah, I will do that like now, or today. Not right now, but... All right, so I wanted to just address a question that's come up a couple of times. Your text refers to this concept of strain when talking about conformations of organic molecules. One of the ways that it talks about strain is angle strain, and that's related to the fact that in some rings it is impossible to adopt the idealized 109.5 or whatever degree bond angle required for sp3 hybridized carbons. So that's what we mean by angle strain. And then the other kind of strain your text talks about is torsional strain, and I don't really make this distinction. Your text uses torsional strain only to describe the fact that staggered conformation is more stable than the eclipsed conformation. It uses the word sterics to talk about having groups gauche versus anti in a Newman projection to describe how this arrangement is less stable than this arrangement. Oops, I'm totally messing that up. But the origin of both of these effects, what am I doing? The origin of both of these effects is sterics, and sterics is just another way of saying electron-electron repulsion of large groups. Of course, I guess we had another explanation for staggered versus eclipsed, and that was hyperconjugation. But the reason I don't make a distinction between torsional strain and then sterics and gauche versus anti is because they derive from the same basic principles. So there may be a question that you had to do for the study guide was identify the elements of torsional strain versus other kinds of strain. And you should know what angle strain is, and you should be able to use sterics to rationalize the strain that's associated with rotation around carbon-carbon bonds. Because frankly, I think this is torsion refers to rotation around a bond, and this gauche versus anti issue is an issue of that too. So that may muddy the water just a little bit, and I'm sorry, but we're not going to make a distinction between these 2 points. Okay, so I just wanted to remind you that if we have a flat 6-membered ring, the bond angles could be around 108. But if you looked at that ring from the side, what you would see is if it were perfectly flat, all the carbon-hydrogen bonds would be eclipsed with each other. In fact, if we looked in this sort of flat conformation, if we looked down this carbon-carbon bond, what we would see, ring is here, ring is there, all the carbon-hydrogen bonds in the front would be eclipsed, and all the with carbon-hydrogen bonds in the back. And so, if the ring is totally flat, you've got, even though you haven't got a lot of angle strain for the 5-membered ring, you do have this so-called torsional strain due to the eclipsed interactions. So to avoid that, as I showed you, the 5-membered ring is going to adopt what some people call an envelope conformation, so that at least for some of these carbon-hydrogen bonds, if we were to look down a carbon-carbon bond, we would see that at least for some of them, we've got a more staggered conformation than eclipsed. And I'm going to try to show you that that's the case using the Spartan app, where I've got a cyclopentane ring here. And you can see it's not perfectly flat. It's adopted this sort of envelope conformation where, see that okay? Do I need to, oh, we're already there. Envelope conformation where one of the carbons is sort of lower than the others. If we look down this carbon-carbon bond, let's see, gotta get my laser pointer. If we look down this one on the left, you can see it's not perfectly staggered, but it's not eclipsed. All right. There's the CHs in the front, there's the CHs in the back. So at least with some of these carbons, you're able to get some not fully eclipsed situations, though for others of them, it's pretty dang close to eclipsed. Okay? So a 5-membered ring is okay, but it does experience, it doesn't experience a whole lot of angle strain, but it does still experience some torsional strain. So now, anything we want to talk about there? Go ahead.
So is the only carbon ring that can't really like bend itself, is that the one in a triangle?
That's right. That is the only kind of ring that can't sort of pucker and relax the cyclopropane that's in a triangle. Yes, because 3 points define a plane. So what are you going to do? There's no way around it. Yeah. Okay. So now we're going to talk about why organic chemists love the 6-membered ring. And at first, if you draw a hexagon and if it's flat and all the sides are equal in length, then the bond angles have to be 120. So you might conclude, uh-oh, now we've gone past the ideal angle for sp3 hybridized carbons, and now we're even further, so that should be some angle strain the wrong way. And that would be true if the ring were flat. Again, if we drew the ring flat and sort of looked down a carbon-carbon bond, we would have the same problem that we listed above for the 5-membered ring if it were flat. We would have CH bonds on a carbon in the front eclipsed with CH bonds and a carbon in the back. So instead, that flat ring is going to pucker, but it's going to do so in an interesting way. And this is something that you're going to need to get good at drawing. I'll talk to you about how to do that in a little bit. In this puckered conformation, all of the bond angles are around 109 degrees. And then if we look down any of the carbon-carbon bonds, we will see a perfectly staggered situation. All right, here is the carbon in the front. And from our perspective, the proton would be coming out to our right, and the proton that's going down would be going down this way in the Newman projection. In the back, we would see a proton coming straight up, and another headed out to our right but angled downward. And so in the six-membered ring, you can get perfectly staggered carbon-hydrogen bonds, so there is no torsional strain or no steric strain associated with having things that are a little bit too close to eclipsed. Whereas in the five-membered ring, everything was not perfectly staggered. So to demonstrate that, let me show you again in Spartan the six-membered ring. Looks nice and flat. Whoa, how did that happen? Oh, okay. Looks flat from above, but if we zoom in and look at it, let's look down one of these carbon-hydrogen bonds. So just like we did in the drawing on the other slide, let's look down this carbon-hydrogen bond. Okay, and as we do so, we notice here's the carbon in the front. We got a proton that's down and a proton that's up. And then in the carbon in the back, we have a proton that's up and one that's down, but they are staggered with each other. And so there are, and this is true, unlike the five-membered ring, this is true sort of all the way around. So I'm just going to sort of slowly rotate and give you the Newman projection for each of these carbons. And as I do that, I want you to just convince yourself that we've got staggered conformations about all of the carbon-carbon bonds. Got it? All right. So in the six-membered ring, there's no more of this strain associated with the fact that staggered is more stable than eclipsed, because all of the carbon-carbon bonds have this staggered conformation. You'll notice some interesting features of this. Well, hold on. And I could tell you, like if we measured bond angles, you would see that the bond angles here are pretty near perfect for sp3 hybridized carbons. So for the six-membered ring, there isn't angle strain, and there also isn't the strain associated with sterics for rotation around carbon-carbon bonds. So the six-membered ring is a nice sort of environment. Six-membered rings are pretty easy to make in OChem, and it's the best, the most well understood ring system where we understand the most about the conformations of this six-membered ring. So this particular conformation has a name. It's called a chair, and in order to see it, you sort of have to look at it on the side, and then imagine that this is sort of an Adirondack chair where your head would go here, you're leaning here, and you sit there, and then your legs go there. It's not great, but the name stuck. I mean, honestly, your head would be bumping into this hydrogen, so you couldn't actually sit on it. So let's talk about the features of the chair. One of the things that you might notice as we look at this is that you have some carbon-hydrogen bonds that are pointing up or down, and you have others that are splayed out to the side. So we're going to describe here two different kinds of hydrogens. The ones that are angled upward, or rather sort of the ones that are vertical, we're going to call axial. So I'm not explaining this particularly well. Imagine that the carbon atoms of this ring are like a belt around a sphere. And you have protons above that are pointing towards the sort of north pole or are aligned with the axis of the sphere. These are called up axial protons. Then you have protons down here that are pointing towards the south pole of the sphere. They are down and they are aligned with the axis of the sphere, so this would be down axial protons. In contrast, you have other protons that are splayed outward, sort of along the equator of our sphere, and so we call them equatorial protons. Here is an up equatorial proton because it's angled up towards the north pole, but it's equatorial. This is a down equatorial proton because it's angled towards the south pole, but is an equatorial proton. Okay. Do you see the distinction? All right. One other thing. If we look at this ring and imagine it as being sort of distorted from being perfectly flat, then we have carbons like this one right in the front that are sort of at an up position. The bonds leading to it are angled upward, so I'm going to call that an up carbon. And then you have other carbons like this one, which I'm going to rotate around so you can see it, where this carbon is sort of angled downward. The bonds that are connected to this carbon are angled downward in sort of a V. So I'm going to call this a down carbon. All right? Up carbons, down carbons. One of the things that is interesting is that up carbons have up axial protons and down carbons have down axial protons. All right, any questions you want to ask so far? Okay, so let me work through drawing this six-membered ring and some of the misconceptions that people get, all right? So basically you're going to start drawing the chair with a slanted line, and you basically need 3 bonds to begin with. So you're going to angle upward, then angle downward at a slightly larger angle, and then back upward like this. And then to complete the chair, I need to draw a line over here that is parallel to this line. And then I need to draw a line here that is parallel to that line. And then I need to draw a line here that is parallel to this line. All right, so if we number carbons, 1, 2, 3, 4, 5, and 6, in a chair conformation, the bond between 1 and 6 is parallel to the bond between 3 and 4. The bond between 2 and 3 is parallel to the bond between 5 and 6. And the bond between 4 and 5 is parallel to the line between 1 and 2. Right? Now, as we've drawn this chair, our up carbons are 2, 4, and 6. Okay, so I'm going to circle those up carbons with red circles. Those are my up carbons. And each of those up carbons is going to have an up axial proton. So I simply draw a vertical line and put a hydrogen on the end of it. Yeah?
Sorry, so every carbon has an axial and an equatorial.
Right. Yes, every carbon will have an axial and an equatorial hydrogen in cyclohexane. The issue is whether the axial one is pointed up or down. Yeah. Okay, other questions? Yeah.
Will we be converting this information to like cyclopentane, cyclobutane in this class?
Will we be using this? No, because for cyclopentane and butane, no, because the cyclopentane and butane rings can't adopt this conformation. Yeah. They can imitate it, but they can't get to the perfectly staggered sort of conformation. Yeah.
Just a curious question here, but because glucose has an oxygen in the place of one of the 6 carbons.
Yep.
Could that adopt a chair conformation?
Glucose has an oxygen as a six-membered ring with an oxygen in the place of one of the carbons. Can that adopt a chair conformation? The answer is yes, and it does. The glucose ring is not flat, despite what other texts may present to you. Yep. That's what glucose looks like. We'll get to there in just a few minutes. Okay. So the protons coming off of these up carbons, 2, 4, and 6, we're going to call them up axial protons. And I guess I'll highlight those in red to match the up carbons. Okay. Now, on carbons 1, 3, and 5 are down carbons. And I'm going to highlight those with, I'm running out of distinctive colors. I don't want to choose red or green because of color blindness. Pink, okay, that's all right. Pink is good. Pink has been the favorite color of all of my sons before socialization indicated to them that that was not going to be popular anymore. I wish we wouldn't do that. Who doesn't like pink, right? It's just a fun color. All right, at all of the down carbons indicated by these triangles, we've got down axial protons, which I will again highlight in this lovely pink color, which I think on the screen isn't that different from the red color, but oh well. Okay? You with me so far? Up carbons have up axial protons, down carbons have down axial protons. The axial ones are easy. The equatorial ones are more difficult, and you're going to struggle with that, so you're going to need to practice. Okay, so on a down carbon, where we have a down axial proton, the equatorial proton must be angled upward. There's no other place for it, but it's not going to be up like this. That doesn't make sense. And so to draw this realistically, what you're going to do is you're going to draw a line to a proton that is parallel to the purple line between 3 and 2 and between 5 and 6. In other words, equatorial protons are parallel to bonds that are one bond away. Okay, so the bond between equatorial proton on carbon 1, the bond of carbon 1 with equatorial proton is, I'm highlighting it in purple because it's parallel to the other purple bonds. And you can see it's splayed out along the equator, but it's angled upward. And so we will call that an up equatorial proton. Okay? On carbon 3, we have an equatorial proton that's also up, and we need to make the bond parallel to these blue bonds between 1 and 2 and between 4 and 5. So I'm going to draw it like that. Hopefully you can see that we're parallel here. That is also an up equatorial hydrogen. Carbon 5 is in the back. This one's difficult for people to draw, but again, just make it parallel to the orange bonds. That is, skip a bond, and then you want to be parallel to that one. So, for example, I would not draw the equatorial hydrogen that way. That is the wrong direction. I suppose if you want to go kind of Picasso and lose any sense of like perspective and depth in the traditional sense, but we're trying to actually represent how these things actually look. So you want the bond to go here, roughly parallel to the orange bonds. Okay? And those are my up axial protons, which I'm just going to highlight with black squares. I'm sorry, did I say the wrong thing? Those are my up equatorial protons. Okay. And then similarly, I could do down equatorial protons at up carbons 2, 4, and 6. And I've run out of convenient symbols, so we will star. I did use square. I used upside down triangle. I guess I could use diamond, but anyway. These are the down equatorial protons. And you'll notice that they're parallel to, in the same way, parallel to the appropriate carbon-carbon bonds within the ring. All right, that's your tour through cyclohexane. Any questions you want to ask there? Okay, fine. Now we need to start putting other things on the ring. Okay, so let's add a methyl group. We'll draw a chair, and let's put the methyl group, that's an ugly chair. I can remember actually when I took this class in the fall of 2000, before I think some of you were born probably, and in any case, Dr. Savage was having us as a quiz draw a chair, and he was walking around the class telling people that chair is ugly, and he told me that my chair was ugly too. So you'll get it. Let's put the methyl group at an up equatorial position, and we'll continue to label the carbons 1, 2, 3, 4, 5, and 6. Again, carbons 1, 3, and 5 are down carbons. Carbons 2, 4, and 6 are up carbons. All right, so we now have the methyl group at an equatorial position, and we could fill in the other carbon-hydrogen bonds. We don't have to, they're implied, but we could. If we look down the bond between carbon 1 and 6, what we would discover is that the placement of the methyl group at the equatorial position makes it so that the methyl group is gauche to CH bonds in the back, but anti to the ring carbon, right? I'm abbreviating this group here, carbon 5, as R. But, oh wait, did that wrong. In the back is carbon 5, in the front is carbon 2. But do you see that the methyl group is anti to the ring? Okay? Now, what I'm going to tell you now is that the chair conformation exists in equilibrium with an alternative conformation called the other chair. Really creative. And how do you know which one is the chair versus the other chair? You don't. It's just one is the chair and one is the other chair. This also allows you to identify fellow nerds at parties with the following joke, which isn't really funny because you have to explain it. What is, except to the other nerds, what is the opposite of a chair? The other chair. Yeah, see, but then you'll know that it's somebody who knows that joke will have been through an OChem class, and perhaps if they laugh, they will have not hated their experience. So by that you can judge. I mean, maybe you actually don't want to associate with people that took OChem and enjoyed it, and in that way you can also tell. Okay, so how do we get from the chair to the other chair? Well, this is a process that your text, I think, calls ring flipping. It's just rotation around carbon-carbon bonds in this six-membered ring. But the process of ring flipping makes all the up carbons, that is carbons 2, 4, and 6, are going to shift downwards to become down carbons. And all the down carbons are going to shift, in this case 1, 3, and 5, are going to shift to become up carbons. So you have to imagine as though you're sort of grasping this hydrogen or this carbon and your carbon-6, and you're sort of pulling it downward, and then you're taking carbon-1 and sort of pulling it upward. Okay, so this is the fundamental thing that happens when you do ring flipping. And there's another consequence of that process. In the process of ring flipping, equatorial protons become axial, and axial protons become equatorial. But, and this is important, up protons stay up, and down protons stay down. In other words, if you're a proton on a carbon in a six-membered ring, there is no changing from up to down. You can change from axial to equatorial, but you can't change from up to down. All right. So your text will often describe ring flipping, and they will simply draw the ring like this, as though you're meant to see, oh, that flipped. But actually, without doing any flipping, I can draw the ring from this perspective, 1, 2, 3, 4, 5, 6, with the methyl group here. I'm literally just looking at the ring from the left-hand side versus the right-hand side. Okay, that's all that's going on there. I think your text does this as a way to emphasize that, hey folks, something has changed. And I suppose that's okay, but it's not just that you're going from looking at it from a different perspective. Remember, the ring flipping process literally takes carbons 2, 4, and 6, which used to be up, and makes them down carbons. So one way you can work your way through a ring flipping situation is to start by numbering your carbons where 1, 3, and 5 will now be at the up positions, and 2, 4, and 6 will be at the down positions. See what I did there? And do you see how it's different from what we did earlier? I've drawn the chair. Oh, I told you I was going to draw it in the same way, then I went ahead and didn't. Okay, fine. Sorry. Sorry about that. Okay, I'm simply going to put 1 here, 2, 3, 4, 5, and 6. All right, so carbon 1, which used to be down, is now an up carbon. I'm going to show you with a model how that happens, but for right now, let's just work with these guidelines for flipping chairs. All right, so up carbons became down carbons. Let's see, we labeled down carbons with pink triangles. So what used to be down became up, and what used to be up became down. I'm going to actually lose the pink triangles. We don't need to complicate this. Now, let's start with carbon 1, which had a methyl group on it. This group used to be equatorial up. After the ring flip, it's still going to be up, but what is the up position now that's available to carbon 1? Axial. Okay, good. Notice we did not change whether or not the proton was up. We simply changed whether it was axial. And then we could fill in the other details. Let's just stick with carbon 1. The proton that was down axial is now down equatorial. On carbon 5, the proton that was up equatorial is now up axial. And on carbon 5, the proton that was down axial is now down equatorial. Similarly, on carbon 2, the proton that was up axial is now up equatorial. The proton that was down equatorial is now down axial. That is what happens in a ring flip. One thing to notice about the ring flip, if we look down the bond between carbons 1 and 6 again, I'm going to fill in the protons so that we can see them. In the front, we would see a methyl group pointing upward. That's our up axial proton, and then our down equatorial proton, and then the ring carbon 2 is here. Right. In the back, we would see a down axial proton and an up equatorial proton with carbon 5 here. Notice now that with the methyl group in an axial position, the methyl group is no longer anti to the ring, it is gauche to the ring. Used to be anti, now is gauche. And so what would you predict? Axial methyl group more or less stable than equatorial methyl group? Equatorial should be more stable, and in fact, the free energy change upon going from equatorial methyl group to axial methyl group is in the upward direction, less stable by about 1.7 kilocalories per mole. Now, for those of you playing along at home, 1.7 is a number you've seen before. I told you that was the A value of a methyl group. It gave you a sense for how big the methyl group. This is where that number comes from. They measured how much worse it is to have a methyl group axial versus equatorial. The A stands for axial, and that's the reason. So there is, in the axial conformation, there are two problems. One is the gauche interaction with the ring. And the second problem is that the methyl group is actually big enough to start to bump into or make steric contact with the hydrogens that are 1, 2, 3 bonds away. 1, 2, 3, or here, 1, 2, 3. We call the idea of the methyl group bumping into protons that are 3 bonds away, other axial protons, unfavorable 1,3 diaxial interactions, and both of these are really steric issues. Okay? 1,3 diaxial interaction refers to the fact that on carbons 1 and 3 you have axial substituents. 1 is a methyl group, and it's going to knock into the other up axial hydrogens. Okay, so let's illustrate that again with Spartan. Actually, we want to go here, and we're going to add a methyl group. And it automatically chooses the equatorial conformation. Okay. Here they're setting the equatorial conformation at 0 kilocalories per mole. And we can switch it to become the other chair, and that's up here at about 1.7 kilocalories per mole. kcals is on this side, joules is on this side. Chemists like kilocalories per mole for historic reasons, but I don't know why. If you prefer joules, that's fine. But if you tell me a number in joules, I'm going to have to think for a few minutes before I can convert it into kcals and then tell you know what I'm talking about. All right, this is the axial conformation. Notice in the axial conformation, this is the equatorial conformation of the methyl group. Notice that the methyl group is anti to the ring in this conformation. Now we're going to switch. Pay attention to the carbon that's attached to the methyl group. It used to be a down carbon. We do the ring flip, and there's not there. Okay. We do the ring flip, and now the carbon that bears the methyl group is up instead of down. The methyl group is axial. Notice that it is gauche to the ring. Also notice that the methyl group is sort of, especially the proton from the methyl group, is pretty close to the other axial up protons. And that is one of the reasons why, actually, if you look at that carbon, do you see how that methyl group is not perfectly vertical axial? It's kind of leaning just a little bit. That's to avoid the steric problems. It may be difficult to see these steric problems, so we're going to go to a space filling model. Do you see there how the methyl group proton is basically making contact with the other axial protons? That's the 1,3 diaxial interaction that's a problem. And then here is the bond between the carbon that bears the methyl group and the next one. Here is showing the methyl group that's gauche to the ring, and there's also some contact there. So that's why having the methyl group axial is unfavorable. As to any questions you want to ask about that? I'm sorry, I thought somebody was raising their hand, so I went to point to them, and now I'm just waving at all of you. Okay. Right? Yes?
So just to clarify, the reason why it's called 1,3 diaxial is because the methyl is on 1 and then the hydrogen on 3.
Right. No matter which way you count, if methyl is on 1, carbon 3 has an axial up substituent. Yeah. All right. So the process of changing one chair to another, you can go actually on the internet and find movies of this. I'm going to attempt to show you using the Molecules app, but it's probably not going to go that well. Basically, what we have to do to get to the other chair is we have to take this hydrogen in the front, this carbon in the front. I'm going to grab it and pull it upward. And it didn't want to move, did it? So, and now we flipped over, so now we can't tell what's up and down. Let me try that again. Carbon in the front, I'm going to yank it downward. Now, do you see how that carbon that used to be up is now down? I wish we could label things in this app. We can't. But if we do this again, you're going to see that the protons that are axial here, the up axial protons, are all going to become up equatorial. If I can, yep, now I'm going to do it again. I'm going to take this hydrogen and swing it upward vigorously. Whoa. Okay, do you see now that the protons that used to be up axial are now up equatorial? Okay, and this is just by rotation around bonds. Go ahead.
So is there really like a determination between like what is an up carbon and down carbon? Because if you like took the ring and like flipped it, then
Is there really a distinction between up carbon and down carbon, right? Because if you took the ring and simply flipped it over, they would all change. No, there isn't. But once we start adding more than one group to the benzene ring, one side of the molecule might not be identical to the other side. I said benzene, but I meant cyclohexane. I'm sorry. As we add more than one group to the cyclohexane ring, both sides of the molecule stop being identical. Yeah. And even when we add a methyl group, I guess both sides aren't identical anymore. So really, the best way to manage drawing chairs is to pick one orientation and stick with it. In other words, do the ring flip, but don't also do what I'm now calling the pancake flip. Okay? All right. All right, so now we can start to deal with a couple of issues. That is, what happens when you put more than one thing on a six-membered ring. I'm going to start with the following molecule. Do we dare? Sure, why not? All right, and I'm going to start by calling this carbon with the OH group 1, 2, 3, 4, 5, and 6. one of the parts of these of chair questions that often students don't appreciate is the part where you go from a flat sort of drawing to the chair, whilst keeping everything in the right place and with the right, what you'll later learn is called stereochemistry. So if I'm going to call, what I do is I draw a chair. I first have the flat sort of drawing, and then I number the carbons of the ring. And then I draw a chair, and it doesn't matter where I start, I'm going to pick a place to start. Let's call this carbon 1. Now as I go around the ring, I'm going to make sure that if I went from 1 to 2, 2 to 3, 3 to 4, and so on in a clockwise sense, I'm going to do the same thing here. And at that point, once I have up and down carbons set, I'm going to fill in the non-hydrogen groups or substituents that are on the ring. At carbon 1, the OH group is up. So in my chair, the OH group must also be up. Carbon 1 is a down carbon. So what is the up position for a down carbon, for a substituent on a down carbon? Equatorial. So I have to put the OH group here. It would be incorrect to put the OH group here because it's not down, it's up. So, and remember in the chair conformation, we're looking at things from the side. So this is up and this is down. All right. Now we can tick along to the methyl group, which is on carbon 4. Carbon 4 is an up carbon, so the methyl group should be where? It should be the up axial position. Good. It would be wrong to put it equatorial. Now, when I write these questions, I often ask, what is the most stable chair conformation of this molecule? And I will, of course, show you options, but what some people do is they immediately do something like this: 1, 2, 3, 4, 5, and 6. Well, the most stable conformation is the one where everything's equatorial, so I'm going to put the methyl group equatorial. Why is that wrong? It's not even the same compound anymore, right? Because in our compound, the two groups, OH and CH3, were on the same side of the ring. Now they're on opposite sides. Those are stereoisomers of each other. That's a term we're going to learn later today. They are not the same. And they're also, we're going to learn, not mirror images of each other. So the word we're going to use to describe these is diastereomers. This one has the group cis, this has the groups trans. Okay? I am warning you, some of you will make that mistake. I hope you don't. But if you don't pay attention, you will, because you're going to remember, you're going to have memorized, oh, equatorial's better than axial, but you're going to misapply that principle. Because remember, the first thing you got to do to get to the chair from this flat drawing is make sure you keep up groups up and down groups down and put them on the right carbon. It's only after that that you consider which is the most stable chair. Go ahead.
So you started with the one carbon on the down carbon.
Yep.
If you start, you'll probably give us confirmations where it's like the one carbon is one of the middle up carbons. Right?
Yep.
And then it's less stable because the OH would be axial.
Well, let's think about that actually. So we could start with carbon 1 on an up carbon. And what would that do to our chair? Well, the OH now would be up axial, and the methyl group would be up equatorial. And that's just the other chair. So people get nervous. They're like, oh, what if I don't draw the most stable chair to begin with? Doesn't matter as long as you can draw the other chair and get the up and down relationships right. Then you can choose which is the better chair.
Which would be the better chair?
Which would be the better chair? Well, the A values for those individual substituents are as follows. For the OH group, it's 1 kilocalorie per mole, meaning somebody did this same experiment up above, but with an OH group, and they found it's uphill by 1 kcal per mole to have OH axial. In contrast, methyl group is 1.7. So it's worse to have methyl axial than it is to have OH axial. That may make some sense because remember what you're trying to avoid in the axial conformation is not only being gauche to the ring, but also these unfavorable 1,3 diaxial interactions. And it doesn't matter how you rotate around this bond between methyl group and carbon 4, you're always going to have a proton that's close to these up axial hydrogens. In contrast, for the alcohol, it's possible to rotate around that carbon-carbon bond to swing the proton over here, and maybe that decreases the steric problems. Okay, so if it's better to have OH axial than methyl group, we would say that this is the most stable chair conformation of this molecule. All right, so you see the process. You're given this. Your first task is to draw it in a chair conformation, but you must not change the up and down relationships. We're going to call that stereochemistry. You must not change stereochemistry. Stereo is for 3D, so it refers to the shape of the molecule. You must not change the stereochemistry. Up stays up, down stays down. Once you've drawn the one chair, then you got to draw the other chair, and only then do you start asking questions about which one is more stable. All right? Let's just see. I doubt Spartan's going to have this one, but let's see if it can handle it.
On the exam, will you give us A values?
Do I give you A values on the exam? Yes, though in a way you don't totally need them because size of substituents is somewhat intuitive. Let's see if we can. Okay. Stop conformer search. Oh, interesting. All right, so the lowest energy conformation, do you see that? The OH group is axial. The methyl group is equatorial. It's choosing another conformation where do you see how it's better to have the proton oriented away from the other axial protons than towards the middle? But everything is still that chair. And then here's a conformation where the methyl group is axial, and that is about a kcal per mole less stable than the conformation where OH is equatorial. And that is exactly what we would have predicted from these A values. It's almost a kcal per mole better to have OH axial than to have methyl group axial. All right. So we need to talk about some other substituents. We probably want to do another example problem on that issue, but we also need to start talking stereochemistry. So let's take a few minutes and then we'll come back and keep trucking along.